All right, so we're going to continue on with exploring Chapter 7 with Bayes' theorem at the office again. I unfortunately spilled water on my Mac, so it's drying right now. I'm hoping it comes back to life. Right now I'm using my office computer, so I'm really thankful I have that available. Anyway, that's some of how I've been doing. I hope you all are doing well also, and not spilling on your computers if you have a computer. Now, quick announcement is that there will be a writing assignment where you have to do some of these problems with Bayes' theorem, and probability. So that's going to be due to me by email, and I'll also have some discussion questions that you can give responses to, and that'll be your participation. So last week I combined them. This week they're going to be separate. So not a whole lot new. So we're going to keep plugging on. I still have to be working on your papers. I'm just trying to keep up with making these video lectures for y'all. So let's get right to it. Okay, so basically what we're going to do in this video is go over the two problems that I gave in the base rate fallacy. So we already did problem 1, and the answer is here for you. So I'm going to do problem 2 with y'all now. Now the problem 2 basically just said to do the same thing, but what you're supposed to do is imagine that you're tested a second time. So for those of you, it might have been hard to figure this out, so you have to think through it carefully, exactly what's different if you're testing it a separate time. Well, we can keep the variables the same. Let D be I have the disease, T be I tested positive. So that'll be pretty straightforward. We're going to use the same Bayes' theorem, but and here's how we calculated it last time. And we ended with your probability of having the disease after you tested positive, given that information from that problem, to be 0.0098039. So still a very low chance that you had the disease, even if you tested positive with a test that gets it right 99% of the time. And that 99% of the time, it says you do have the test when you do have the test. So, sorry, you do have the disease when you do have the test. You guys know this from last time. So what exactly is different when you're testing the second time? Well, the prior probability, the probability that he had the disease, was really, really low, right? 0.00001 or something like that. Now your prior probability is different. Your prior probability of having the disease now is now up to this. It's not 0.0001. It's going to be 0.0098039. So your prior probability changes. So that's going to be the key difference. So the test, it's still going to be the same here, and here it's still like 0.99 accurate. It's still got a 0.01 chance of saying you have the disease when you don't. And so that's going to be the main difference. So now we can just easily change these. Okay, so basically the only thing that changes is the prior probability. And what is that? It's a horrible number, but it's going to be 0.0098039. So 0.0098039, and that's going to be also 0.0098039. Okay. Now, if the probability of D, the prior probability you have the disease, was 0.0098039, that means the probability of not B is going to be 1 minus that. So now what is 1 minus that? It's kind of hard. I just used a calculator, and I got it already, and that is, it's going to be a point, let's see here, 0.9901961. Okay, so that's going to be the difference. And then now we have to change these. So really, this is a horrible problem because of all these decimals. I don't know what was going over me, but I wanted you guys to get more practice. So, all right. So now you just have to multiply. Just put everything in your calculator. I doubt most, probably all of you, I'm sure none of you can do this in your head. But this number, 0.0098039 times 0.99 is going to be 0.009705861. Okay. This number, 0.0098039 times 0.99, well, those are the same. So that's, thank you, Lord. 0.009705861. Okay. Plus, now we have to do this multiplication. 0.9901961 times 0.01 is going to be, what's that going to be? 0.009901961. Again, I'm so sorry for this horrible problem. I promise for your test, the numbers will be a little easier at least. Okay, now we have to add these. These two numbers will add up to, so this is going to be 0.009705861. And adding these is going to get us a 0.019607822. That's what you get. And then what's this? This is going to equal 0.49499. Okay, so that was a lot of work, but basically at the end of it all, if you take the test a second time, so if you take the test a first time, you only have about a 1% chance of having it. Okay, if you take a test second time and you test positive, then you got about a 50% chance. Let's say you tested positive again, well, it's going to be, we could probably just round that to 0.5, but I mean, it's going to be even higher. So that's kind of how the math works for this problem. All right, so let's go straight to, well, let's see. Yeah, let's just go straight to the next problem and do this all in one video. So the next problem was, and I'm going to call it up, go to the base rate fallacy handout. It says, you're wondering, I made it as similar, and there's other ways to talk about Bayes' theorem other than testing for diseases, but this, I'm just trying to get your feet wet to help you think about it. And I'll try to make the whatever I test you on, it won't be too different from these practice problems. Of course, eventually, if you were going to explore probability theory and Bayes' theorem more, then you would want to become more adept at problems different from this, but I'm just trying to be nice, I guess. So, all right, so it's going to be another disease test again. You know what I'm doing for diseases? We could also do for pregnancies. We could also do for whether you might have a virus. I mean, you could use this sort of reasoning for coronavirus as well, like if you tested positive. You'd also have to take in the prior probability that just anybody has a coronavirus. So, okay. So you're wondering whether you have another rare disease. You take a test that's 80% of the time correctly says you have the disease if you have it, and 70% of the time correctly says you don't have the disease if you don't have it. Okay, the disease is present in 3% of the population. Okay, so that's going to be your prior probability. Okay, you take the test and it says you test positive for the disease. What's the probability that you have the disease given that you tested positive once? Okay, so let's work through this together. The prior probability that you have the disease is going to be 3%, so 0.03. Okay. Times, now it says you take a test 80% of the time correctly says you have the disease if you have it. So given that you have the disease, D, it'll correctly say you have the disease 80% of the time. The nice thing about this is these can repeat, so. All right, now this is the harder one. 70% of the time correctly says you don't have the disease if you don't have it. Okay, so, all right, well, actually, let's do probability of not D first. So the probability, your prior probability that you do have the disease was 0.03, right? then the probability, prior probability that you don't have the disease is going to be 0.97. Okay, so this, like last time, the probability that we can do, whoops, where am I? Okay, so the probability, or it'll 70% of the time correctly say you don't have the disease, not T. If you don't have it, not T. So that's 0.7. So that means the other percent of the time, it'll say you do have the disease when you don't have it. That's going to be 0.3. All right, so that's going to be 0.3. All right, so that's setting up the equation. And you know, if I give this on the test, I'm going to care more about you knowing how to set the equation, although you should get the right answer too. So let's see. Oh, so I wrote it here, the answer. So 0.03 times 0.8 is going to be 0.024 divided by 0.024 plus 0.97 times 0.3 is going to be 0.291. Okay, put all this together and it's going to be 0.07619. Okay, so for this test, not nearly as good. It's got an 80% and 70% correction rate. But when you take the test, your chance of having the disease is 7% or 8%, you know, around 7 to 8%, which is higher than the other test that had a 99% likelihood. And what made the difference? The prior probability that you had the disease in the first place. So the more rare a disease, the less good the test is going to be. All right, so that was a bit messy, but you're gonna have to know these sorts of problems. The only way to learn this stuff is to practice it, and this is the most math our class is gonna be for the most part. So, all right, with that, we'll end this recording, and then we're gonna apply this all to the fine-tuning argument, which is what I'm excited about. So that's for next video, bye.